So hello everyone, today I'm doing my student lecture about the resistance and powering. We will talk about the chapter just before the one we talked about here, resistance and powering. In this presentation, you will see three different themes: the model basin theory, the dimensional analysis, and the ship resistance prediction. First, model basin theory. The basic idea is to predict the speed of a ship by using a model test. Because during a long time, it's quite complicated to get the real speed of a ship only using a model test. Until William Froude in the UK in 1868 discovered what was really important. He realized that there were two major resistance components that behaved differently when scaling up from model size to real size. He developed a procedure to treat friction and wave making separately using the laws of similitude through dimensional analysis. The laws of similitude are about how physical characteristics are affected by scale, and the dimensional analysis is the study of the relationship between physical quantities with the help of their dimensions. Here we have a picture of William Froude and the Admiralty's first naval tank. You can see here a long water tunnel, and here a machine that makes a little model ship go forward through the canal. For example, here for the dimensional analysis, we have a simple pendulum. As said before, the dimensional analysis is a functional relationship between a set of non-dimensional groups. Using the primary dimensions as the mass, the length, and the time, we can predict all kinds of kinematics of this pendulum. Here, in instance, we have the mass, the length, and the acceleration of gravity. Here we have a simple representation of the dimensional analysis. It makes it easy to understand its purpose. Here we will get an orange circle, and here it has to be this one to get this result. This way we can have ratios between units, like a ratio to get from meters per second to kilometers per hour, or from miles to meters, especially in Navy area. To apply this to the shipbuilding, we need these physical functions as the fluid density, the speed, the size of the body, fluid viscosity, gravity constant, and the pressure. This way we can find out primary important parameters for the ship. According to Froude's hypothesis, dynamic similitude for both friction and wave making cannot be satisfied at the same time. The practical method is to deal with the frictional and the wave making resistance parts separately. So we have this equation that gives us Froude's hypothesis. The total resistance here, Ct, is the sum of the residual resistance plus the frictional resistance. Froude number. So first, for the residual coefficient, which is Cr, we know that ships of different sizes, here we talk about the difference between the model and the real size ship, they will have the same residual resistance coefficient Cr if they are moving at the same value of this parameter, dW divided by GL. V is the speed of the model or of the ship. G is the constant of gravity acceleration, and L is the body size. Such speed is called the corresponding speed. So the fluid number is this parameter. It is the square root of this one. Here we have a short video to explain this number.
In liquid flows with free surfaces, the Froude number compares the speed of motion to the natural speed of gravity waves. A ripple tank demonstrates motion with a Froude number less than 1, equal to 1, and greater than 1. In the last case, surface disturbances are left behind, forming swept-back waves. This duck is swimming at a Froude number greater than 1, producing a similar wave pattern. There's a strong analogy between these liquid surface waves and shock wave phenomena in supersonic gas flow, where swept-back waves occur when the Mach number is greater than 1. The Froude number is also important in open channel flows, such as the spillway downstream of a dam. In this experiment in a water channel or flume, the fast-moving supercritical flow downstream of the spillway causes erosion of the riverbed. In this flow, the Froude number is the most important dimensionless parameter to match between the model and the full-scale spillway. The Reynolds numbers don't match, but it doesn't matter.
Here we can see one of the situations that was mentioned before in the precedent presentation and in the video. Here we can see a dam and the water flowing from the dam into the valley. First we have laminar flow and it ends in turbulent flow. And between these two we have this hydrogen. The Reynolds number will change from here to here, and as said in the video, turbulent flow here will cause some erosion on the seabed. So for the frictional resistance coefficient, first for a deeply submerged body, which means submarine, the frictional resistance is dominant. We have this equation giving us the frictional coefficient. It is function of this number VL divided by nu. And this number here is the Reynolds number. We know that V is the speed, like before, L the body size, and nu is the fluid kinematic viscosity. To predict the ship resistance, we have several steps we can follow. Now we will see the 8 steps to get the results. First, the model is made to a linear scale ratio, which is lambda, and will run over a range of corresponding speeds. For lambda, we have the ratio between the real size of the ship divided by the model size. After that, we measure the total resistance of the model. Then we can calculate the frictional resistance of the model, and assuming the resistance is the same as if it were a flat plate, a smooth flat plate having the same length and wetted surface area as the model. With RTM and RFM, we can have the residual resistance here for the model. And using the linear scale ratio lambda, we can calculate the residual resistance for the real set ship. And one of the last step 6, to get the frictional resistance of the ship, we need to calculate it using frictional coefficient charts that I don't have in this presentation. And finally, with these two, we get the total ship resistance, by summing this. And we can also have the power requirement, which is the multiplication of the total ship resistance and the real size ship speed. Especially if you work in the naval field, you will usually use this method to get the results. We can explain the different resistance types. The first one, frictional resistance, is due to the motion of the hull through a viscous fluid. The wave-making resistance is due to the energy that must be supplied to the created wave. Eddy resistance is due to the energy carried away by eddy shift. Air resistance is due to the aerodynamic drag acting on the above water part of the ship. And the residual resistance is the sum of the wave-making resistance and the eddy resistance. Extrapolation of ship resistance. This is a graphical representation of the frictional resistance coefficient here on the vertical axis. And on the horizontal axis, we have the Reynolds number. Here we have the CF line, which is the frictional coefficient. Here, this is the number for the model, and here it is for the real section. Above, we can see two curves, which are both the total resistance coefficients. The first one here is for the model, and the second one here is for the ship. On the graphic on the right here, we have the same representation, but displayed differently using the wave making and also the eddy resistance to display the same results. Tank experiments. We know that the wave pattern is similar to the full scale, real scale situation. There's also another observation. The shape also is similar of the wave in the model and in the real size. But there's something other that's different. It is the time scale. It will be smaller in experiments because it is proportional to the square root of the body size. Hull speed can be calculated by using this formula. Another video. Here, model to drag the here you can see some wave. As the duck was going before, you can see here also that the fluid number is bigger than 1 because of the wave line. you. This is all for the